Ladies, so last time we left off talking about an action potential, right? How a neuron works. Today we're going to talk about how they communicate with other neurons or other cells. So yesterday we talked about action potential, just simply the movement of sodium ions in during depolarization and potassium ions out during repolarization. So it'll look like this. Sodium rushes in, potassium rushes out, and then you get a recharge, and the action potential just travels down the axon till we get to the end of the neuron. So we'll bring it, and so now the thing about yesterday we saw that there are two types of neurons. The neurons that are coded, and there are ones that are not coded. Okay, so this is an example of a neuron that's coded. It's got a myelin sheath. Okay, so the myelin sheath refers to that coating, which I said to you is like the plastic coating on wires. You'll notice that there's gaps in the myelin sheath. So the thing about a neuron that's myelinated, and see if you can figure this out, it's actually faster than a non-myelinated or unmyelinated neuron. Why do you think it's faster? You look at this picture, what do you notice about the action potential in this area actually doesn't, if you recall the way the action potential travels, like a domino effect, you saw that basically one area triggers the adjacent area, right? Which then will trigger the next adjacent area. Why are myelinated neurons faster? If you look at the picture, what do you notice? This area does not actually trigger this area, it triggers the next exposed area. So you're actually skipping some steps here. So then this area will then trigger this area, which will then trigger this area. It's almost like the action potential jumps. We call that saltatory conduction. Okay? So a myelinated neuron is faster because it doesn't have to trigger all those areas. But in any case, the neuron gets to the end. So when it gets to the end, what happens? So what we're going to talk about today is synaptic transmission. Okay? What actually occurs at the synapse, which is the connection between one neuron and another neuron, or between one neuron and a muscle. Okay? So the synapse is going to look something like this. So here you're seeing this is the cell that would send information. This is the cell that would receive the information. So if you look at this picture over here, you see a neuron right here, and it's making, there's other neurons that are making contact with it. So one neuron is going to send information to that neuron, and we're going to talk about how that works. Okay? So the chemical that comes out of the neuron that sends out the information, that chemical is called a neurotransmitter, which you can see right here, okay? Neurotransmitter. That's the chemical that is released from the neuron that sends out the information. Now, we're going to focus on what's called the chemical synapse. There is something called an electrical synapse, where the connection between the two neurons is very tiny, so that the action potential can actually travel directly from one neuron into the next one. So in this picture here, remember, an action potential is, it's graphed as the up and down movement of the voltage, right? You can see here, the action potential just travels from one cell into the next cell. That's because the gap is so tiny that the signal does not need to be converted. Okay? So for example, in your heart, the cells are so close together that when one cell is triggered, the action potential directly travels into the adjacent cells. This is fast. This is a really fast form of transmission. But in a chemical synapse, the gap is too wide, so the action potential cannot just jump to the other cell. It has to be converted. Okay? It has to be converted into a chemical. So, for example, if the gap between this neuron in purple and these other neurons is big enough, the action potential has to be converted to some sort of a chemical signal. So here's a picture of that, okay? So if the gap is big enough, this neuron would, if it's being triggered and it's generating action potentials, it will release a neurotransmitter. Now, the way it works is quite simple. The action potential gets to the end of the neuron, which triggers what's called a calcium spike. Okay? So you can see it right here. This is the calcium. The calcium spike is the signal to release neurotransmitters. Now, in cell biology, this is a common thing. Calcium spikes tell cells to release things. Okay? Remember we talked about what's the most important role for calcium? It's not for building bone. It's to do stuff like this. Calcium is important in cell communication. And you saw that your body is willing to take calcium out of bones to put it into the bloodstream because things like neurons and muscles need it to communicate. So the calcium spike releases the neurotransmitter. In this case, the neurotransmitter is this green dot, which then diffuses to what's called the postsynaptic cell. So here's the postsynaptic neuron. Okay? This would be the presynaptic neuron. And then it targets this gate. Now, this orange dot is sodium. What happens when the transmitter docks with the gate? What happens to the gate? Does it open or close? It opens. Now, what happens? The sodium comes in. So what do you think the effect is of this neurotransmitter then? Do you think it triggers this neuron to generate its own action potential? Or do you think it shuts it off? What do you think happens in this case? Do you think it activates this neuron? Or do you think it doesn't activate it? What do you think? Yeah, it does. How do you know it activates the neuron? How do you know it activates the neuron? Sorry? Right, because the sodium is coming inside. And the entry of the sodium is the start of an action potential, right? So in this case, this could be like, for example, acetylcholine. Okay, acetylcholine is a neurotransmitter that will stimulate certain neurons. It stimulates skeletal muscles. Okay? But here's the thing about neurotransmitters. Don't assume that, just like hormones, don't assume they work always the same way. Like acetylcholine will stimulate your skeletal muscles. It will cause them to contract. So when you're moving your body, the skeletal muscles, which are under control, voluntary control, are stimulated by acetylcholine. But acetylcholine on your heart actually does the opposite. It actually slows it down. Okay? Now, can anyone spot a problem though? We talked about this yesterday. Acetylcholine will open up the sodium gate. So acetylcholine on the sodium gate leaves the gate open. What's the problem? Remember, a neuron fires an action potential, but then it must fire more. It doesn't just fire one action potential in its life. It's constantly firing action potentials. So we can imagine this is, for example, your diaphragm, which controls breathing, right? It gets a signal, the sodium gate's open, you get an action potential, muscle contracts, you breathe. But what's the problem here? How do we breathe a second time? What must happen? The cells must what? Recharge. So what's the problem here? What must we remove so we can recharge the cell? Aneke? Beautiful. We need to remove this bad boy right here, the neurotransmitter. So there's a chemical called cholinesterase. Okay, it's an enzyme that is released by the body. It's called cholinesterase, which I believe we talk about it right here. And what cholinesterase does, cholinesterase will remove that neurotransmitter so that the gate could close and it could recharge. In World War I, I think it was World War I, they used nerve gas, which would block cholinesterase. And here, we talked about this yesterday, a toxin that keeps gates closed or a toxin that keeps gates open could end up giving you the same problem, right? Because if you keep the gates closed, you don't get the action potential. But if you keep the gates open, you can't recharge. So then you don't get the action potential. Anyways, so that's an example of how this neurotransmitter would work. Now, not all neurotransmitters work the same way. Okay, so I want to just quickly point this out because as you're seeing in this diagram, a neuron does not receive one signal; it could receive many. So look at this picture here. Okay, so we have three neurons called A, B, and C. And A, B, and C are targeting neuron D. Okay? They each send a signal. And the thing about neurotransmitters, they come in two types. The neurotransmitters that try to stimulate other neurons, and then there are neurotransmitters that try to inhibit. Okay? So imagine you're a neuron and you're receiving messages that say two things, fire or don't fire. How do you decide what to do? How do you decide as a neurotransmitter if you're going to fire or you're not going to fire? What do you think the answer is based on this picture? So some of the neurotransmitters will try to promote an action potential, and some of them will try to inhibit. Actually, let's pause this for a second. All right. So what do you think? Notice neurotransmitter A and B. Okay? Neurotransmitter A and B bumps the voltage in a positive direction. Neurotransmitter C bumps the voltage in a negative direction. Remember, the neuron has a resting voltage. But to trigger an action potential, which way must the voltage move? Up or down? If you recall the diagram of the action potential. So it starts off at a particular value, like negative 70. The voltage has to go which way? Up or down? Towards the positive end, right? Or less negative. So, what do you think is happening then here? Neurotransmitter A is trying to promote or inhibit an action potential. Promote. Yep, because it's trying to bump the voltage to that magical value, that threshold value. What about B? Promote. What about C? Inhibit. Any neurotransmitter that pushes the voltage away from that threshold will try to inhibit. So then how does a neuron decide? It's just simple math. Each neurotransmitter is going to change the voltage, right? If the voltage change is enough to get it to threshold, then it will fire. So for instance, if neurotransmitter A is plus 10, and neurotransmitter B changes the voltage by plus 10, that's plus 20. And neurotransmitter C changes the voltage by minus 5. The total there is plus 15. Now, if the resting state is minus 70, for instance, sorry, I don't have a pen here, and the threshold is minus 55, what's the difference between those two? Plus 15. So if it's enough to get it to threshold, then the neuron fires. So it's just simple math. The neuron uses simple math to decide if it's going to fire or not. If the voltage changes to threshold, it fires. So that means we have two types of neurotransmitters. We have ones that inhibit, And what they do is they hyperpolarize the neuron by making them more negative. So for example, GABA. GABA is a neurotransmitter that promotes the entry of chloride. Now let's think about this for a second, okay? What's chloride's charge? What is it? Chloride is what? Negative or positive? Negative. So if the neuron is already negatively charged, and we put in more negative ions, which way does the voltage in the neuron go? Towards threshold or away from threshold? It's away. It's further down. So some anesthetics will work this way. Some anesthetics will hyperpolarize the neurons so that they are so far away from threshold that they don't get stimulated. And that's good. Why would you not want those neurons to be stimulated if it's an anesthetic? Because you don't want to feel what? You don't want to feel? Why does someone take an anesthetic? You don't want to feel pain. Okay? You don't want to feel pain. Now, so you can see in this case here, right? This is acetylcholine. Look at what it does. It removes positive ions. So what would this do to the voltage in the neuron? If positive ions are leaving, which way would the voltage go? More negative or less negative? More negative. So positive ions leaving is exactly the same as negative ions coming in. It's exactly the same. So acetylcholine could be inhibitory. Now this would be the effect on the heart, okay? Then there are neurotransmitters that do the opposite. They're excitatory. So what they do is they try to promote action potentials. So for example, maybe in this case, norepinephrine will promote the entry of positive ions. Now what happens if positive ions come in? Voltage would go which way? Up or down? It would go up, closer to threshold, easier to fire. Okay? So I think we'll wrap up there. We talked about the communication between neurons, and we talked about neurotransmitters, and then we talked about the two types of neurotransmitters and how a neuron decides what to do. Okay? We'll end there. The end.